Hello and welcome back to Repair-A-Thon Halloween edition. So the vote was 1,000,000 to 1 that I should repair my remaining yellow board. Here we have 3 of them. But before I get there, there is still one red one of the clock boards. Yes, this is the Repair-A-Thon yet again. If you follow the channel, you know that we are trying to revive no less than 6 of the real-time clock interfaces for the HP 9825 calculator. At 2 boards apiece, 1 clock and 1 interface board, it's 12 boards to repair, and when we started, we had nothing working. In the previous episodes, we were able to repair all of the clock boards but 1, which caused emission of magic smoke from the interface board it was attached to. There was a weird short that we attributed to the nanoprocessor, but we could not really measure it, and all in all it was very weird, as you'd have expected the nanoprocessor to release the smoke before its supply on the other board. And the viewers also noticed that it didn't make any sense, so I put my bad short processor in there, and interesting enough, this time I had another kind of short. I had a short in the reset circuitry. So then I started looking what could cause shorts on that thing, and if you look at it, there is no corrosion on this one at all. So I said maybe it's the connector, and then finally it dawned on me that under this connector there is a golden trace. I was using these really long pins, and of course when I put it in there, it pokes on the other side and it touches on this unisolated ground thing. So I'm going to change this, turn them around so they have the short side coming in that. And I bet you the HP engineers were also bitten by this. On the Rev A and B boards there is no such trace. On the Rev C board, of which I have only one, the trace suddenly appears. But on the later Rev D, they quickly added a solder mask to it, so it would not be shorted by the HP connectors, which also use very long pins. So here we go, we're in our test configuration. I'm confident enough that I don't have a short anymore. I just wired it correctly. And sure enough, it's 9 volts, so it works. And over here it's saying no time lost, which is normal, should have error 16. Oh, 48, that's not good. So this one has yet another failure mode where, no, I did set it manually with the buttons to a time, and I ask it to read the time, and it's trying to read the time. And if I come over here and do a read, although it read the time, it actually couldn't, so it cannot read the time from the chip, although it was commanding it correctly. I think I found that we know it's a read problem, so when the processor wants to read, it strobes these tri-state buffers, and basically what's on that side comes out on the other side. So I tested all of these gates, and sure enough there's one that doesn't work. So is that chip down there, that's the little tri-state latch. Do a reset, and eventually it's going to try to read it. That's in, out, read. And see if we can get another one. Then you have to get a few until you get all the cases. So that's a 1 read as a 1, another 1, a 0. That was a 0 read at a 0 during the pulse. This gate is working, and then if I switch to the next gate, that's the one that's not working. So it's trying to read okay, but that's a 1, came out as a 0. Same thing, 1 came out as 0. What just happens is that is getting 7 segment combination that don't make any sense, because that bit 9 is always at 0. So unfortunately I don't have that IC on hand, so I have to order it and replace it to make sure this is actually the fault. Okay, so that guy gets back to yellow. It's not shorted anymore. Shorting was all my own doing, but it has a fault in it, and we'll know if we bring it to green when we change the IC. So in the meantime, we switch to those yellow boards. So far we have only worked on that board over here, and now we switch to this one, which is the interface board. Alright, interface boards, those are conceptually simple but a little hard to measure. No, first there is still some stuff that kind of belongs to the clock board, the 1 MHz quartz that we wrestled with in the previous episodes, the 9-volt power supply and reset circuits that gave us the magic smoke. But most of us is concerned with joining two buses, the bus of the calculator and the bus of the nanoprocessor. And of course, both sides are asynchronous, so you need to find a way to synchronize them. And that's done with these magic parts here, which are the heart of the card. And those are tri-state latches. So basically what they do is that when there's data that needs to go into the card, this is a memory with a gate in and a gate out. So the calculator will gate its data in. It will ping the nanoprocessor on another line called the flag. And then the processor will come back and activate the out gate and read it back. And there is one that goes in a direction, and there's another one that goes into the other direction. What is always complicated in asynchronous stuff is the addressing and the timing. So the addressing on the calculator side is done by those 4 lines, and when it gets a match, it goes out on this line that's called status, and it's reported to the processor that the addressing was successful. So that's the first one we'll monitor. The second one that's important is the handshake. That's the flag. So after the data is latched, the calculator lets the nanoprocessor know that it has something to get, and it's the flag line. Where is it? This is the flag latch. So we'll monitor that one. It's this line coming out. And once the processor has read the data, it will reset the flag. So we should see if a transaction is working, then the flag should come back and back down, or down and back up. And on the nanoprocessor's side, it's actually simpler. They are just 2 lines. There's one that's read and one that's write. Here is read. Read is over here. And you can see it goes in and opens this one. And there is a write. Write is this fellow. There we go. So these are the 4 lines we should be able to monitor and get a sense if the transactions are happening normally. I have now hooked myself up to the interesting lines. Interface select, flag, read and write, or write and read. And let's do an IO transaction. So this is going to ask at the time it's going to respond. So there's going to be activity both ways. And here we go. We just see it. So this is a working card. So of course it works as expected. You can see that at the beginning of the series of transactions, the select signal goes on. We can address our card. And then this is the flag. This is basically when it goes down, the 9825 tells the nanoprocessor something has happened. And the nanoprocessor responds when it's done with it. You can see that, for example, here is one that took a little while. So here, the 9825 wrote something, and it took a little bit of time for it to respond. Here it wrote something else, and it took longer time, so it was busy doing something else, processing this command probably. And now you can see those are write transaction in the other direction. It's pulsing the red line, and it responded with a whole bunch of characters, which is the time read. The next step to this is to try to intercept what data they are exchanging and make sure it's the right one. And for that, we're going to use our trusty logic analyzer. So on the logic analyzer, the trick here is to only look at the bus at the relevant time. So I'm monitoring the read and write lines the same one as I have on the scope. Finally I arrive at what I was wanted. It's in the trigger. I store the data only when there's a read or a write, and let's look at it. So let's read the clock. Read clock. And we caught all the transactions over here, and it's still doing it. It doesn't know that's ended. And there we go. Now you can see what information was exchanged. So the processor read R, carriage line feed. So those were the three transactions we saw over here. See the three reads. That was R, carriage line feed. We now know. And then later on the red ones, there is the answer, and we'll see what the answer is. It answered 06, 05, 20, 26, and one didn't catch the last one, I think. And see what it responded. Oh no, it's a double one, so that's why. So it's 06, 05, 20, 26, 11. Is it a double? Yeah, it's a double. It's twice as long. Which we can see in the listing. It might be easier. There we go. And then we have the result of the transaction. Read clock carriage line feed. Response. Months June, 5th of June, 8 p.m. 26 minutes, 11 seconds. So we are instrumented. We are ready to debug the boards that don't work. Okay, I've connected one of the bad boards. Actually, this is the board that has the most life. It responds, but it gives me blank responses. I double checked everything, but these are always the smoky moments. No smoke. Flag one up. And should be reading the clock right now. Alright, I see a transition here. It is doing something. This one gives me error 48, even with a good board. If I do a transaction, for example, error, give me error 32, and if I look at the scope, it just did the right things, and the 3 character got one back. If I look over here, error, carriage line feed. Oh, that's not an ASCII character, so it got 32 back and doesn't know how to display it. So the transaction is okay, yet it makes the board fail. It makes the clock board fail. That is so weird. I have the problem with the clock chip, which used to work fine. Oh no, we're victims of the voodoo again. So this, I put my LED display on the clock chip, and when it tries to set the time, it gets stuck. And this one worked a second ago. So I swapped the clock board for one that now works, and the interface cards confirmed good. So none of my doings, just the voodoo. Board 1 is suddenly yellow, and this one repaired itself. Go figure. Alright, let's get to our second board over here. I had written on it, it hangs, it doesn't do anything. And basically it was a flatliner on all of the lines except the select. The flag wasn't even up. So I checked, and the processor wasn't doing anything, wasn't even trying to read the clock. I quickly figured out that it must not have been powered in one of its lines, and I'm on the 9-volt line here, and it reads 0.7. So either I destroyed it, or the little reset circuitry and the 9-volt power is not working, which is probably the case. So it must be that little guy over here that caused us trouble before. Indeed, that's our old friend that emitted the magic smoke in the previous episode. It serves two purposes: to power the processor with 9 volts, but it also acts as the reset and is driven by a short delay circuit at power up. So I was following my little circuit and this was never turned on because this was never low. Then it goes to the other card and is inverted as the output of this. This is a reset circuit. Here that should start high and go low, and it stays high. I am hooked up right on the pin output of the inverter, which should give me the reset signal going to 0, and it's a solid 5 volts. So it's one of the few boards where we hadn't changed the inverter. That's the same inverter that does the 1 megahertz over here, but the reset gate is bad. So yet another 4069 CMOS inverter that's dead. Okay, so bad. CD 4069 goes out. That would be our fourth one, I guess. One comes in, we'll solder it in and try it again. Okay, it's back in circuit. I'm always nervous because you take things in and out a million times and you're going to break something eventually. Let's see if we have the 9 volt of the processor back. No, we don't. 0.7 volts. Alright. That's no good. And let's check if our reset signal is going to 0 now. No! It's staying there. So what can it be? The input pin is not going up? It's not. It's going super slowly. Now this must be a special Halloween treat. An RC circuit that does not work. All it has is a 75k resistor and a 0.1 microfarad capacitor. I have never seen such a circuit go bad. This little guy down there should be done in a few milliseconds. What the heck? So I am at my wit's ends here. There's a resistor and a capacitor that doesn't charge. How can that be? And sure enough, I haven't seen it either. There's a little bit of the blue death right here. So this is where a ghost is. Bad cap. My goodness, it's another one of those battery leakage that killed it. It goes in the weirdest places. Okay, cleaned up the board, did a little bit of vinegaring, redid the solder joints, replaced the cap. I think I just want to see if I have a reset signal. Yeah, one high, one down. Okay, you can see it quite quickly. Boop. All right, reset signal. Let's rehook the rest. Okay, I rehooked everything. Okay, I have ROM accesses now. This is what this is. I think it was trying to read the chip. It read the time. Okay, we repaired it. So it's fine. There you go, gets the clock. Any errors? No errors. Okay. So we are back in business. So this one, we didn't need any of the complex instrumentation to resurrect it. It's another blue death cause problem, and it's repaired. So let's see if this one comes back to life now. Alright, last board of our series of 3. This one hangs. Oh, it's similar. No processor activity whatsoever. Okay, let's do like the previous one, see if we have some 9 volt power on the nano processor. We do. Okay, so it's something else. We have 1 megahertz, so it would be on the green. We don't. Alright, so that's one where the 1 megahertz doesn't show up. Am I correct? Yep. Okay, let me check the history of that board. Yeah, that board say that we changed the inverter and that it got good crystal. Oh no, yet another previously repaired problem that came back to haunt us again. We previously had fixed this problem by changing out the CMOS inverter chip. How could the new circuit die again? Having no better idea, I changed the circuit once again and it brought the 1 MHz back. That is, until I tried it again in the full setup. And I just replaced the inverter again and it was working. And I put it back here, didn't do anything. And it's gone again. Okay, so I took the second one out, so it's on the third inverter. 1, 2, 3. Yeah, so it works again. And I bet you if I put that card back in the HP 9825, it will kill it again. Because no, 3 times in a row, that cannot be a fluke. Okay, I'm becoming superstitious, so I put my ESD bracelet on, which shouldn't be that necessary. The bench is ESD, it's grounded. And it stopped working when I looked at it. Aha, it just stopped oscillating in front of my eyes. I think I know what's going on. This is an analog oscillator made with a digital gate. The gate is brought to an intermediate linear state by the 10 meg feedback resistor marked R4. I bet you the new chips are just fine, but the 10 meg is too high a value for this chip. Okay, took the 10 meg out, put the 5 meg. And nothing goes. Alright, my circuit didn't die, it's just hard of oscillating with the 10 meg. So this actually measured 11, which is not that far. But that's the problem when you do analog circuits with digital ICs. It's very sensitive on the brand that you get and on what's inside. So maybe that's what happened. I replaced it with one that was made 40 years later, and it's not exactly the same analog wise. Okay, circuit's back in on a good ESD surface, so hopefully it didn't die from transporting it, but I don't think that was that at all. It's nothing to do with ESD. There you go. It has to do with using different ICs. Okay, so I have my 1 MHz back. Let's rehook everything. And my 2 other circuits didn't die, so that's good, comforting. Makes more sense now. Okay, I'm hooked up again, and this time hopefully it will oscillate. I've changed my green trace to 1 MHz. And we have 1 MHz, very good. Oh, and sure enough, the clock has woken up, processor is working. Let's see if it got to read the clock. It did! Alright, that's all there was. Error 0, it's repaired. Whew! Alright, well, for all the fancy equipment we put, which was interesting but not necessary, we repaired our 3 interface boards. They were all inhabited by ghosts. We have a semi-victory here with all of our interface boards repaired. Okay, moving forward, never the way we planned for it, of course. So we have 6 interface boards to green, 1 clock board that progressed from red to yellow, and we think we know what's wrong with it, but also one that regressed from green to yellow, and still don't know what it is. So let's figure that last one out. Some more news on my the former vinegar board that re-failed, and this time it seems to be a different problem. Can't set the chip nor read it, and I checked everything that was connected to the chip, and it seems that the culprit is this guy, the circuit that latches the state of the buttons. And here you can see on top there's a latch signal. This is set and this is read, and if I press reset to get it to read the clock, you can see the read button is normal, the set button is totally abnormal. So it should only change state when there is a latch, and it does change state, but then it hesitates for a long time. That is not normal, it's unstable. So chip U7 is probably the culprit. Alright, so how did we do on this fine night of Halloween, where we got this side pretty green? So, one had a bad reset cap caused by corrosion. One had a flaky oscillator, probably caused by the change of the inverter, and was fixed by lowering a feedback resistor from 10 meg to 5 meg. And one just repaired itself, which is from the ghost, right? Which was compensated by another ghost. We had one that worked before and stopped working. And we also had one that we thought had a short-circuited processor, but not at all. The short circuit was all of my doing. And those are half working, and I identified which circuit is not working. In both cases, it's a circuit that interfaces with the clock chip. In this one, it's the circuit that presses the button. In this one, that's the one that reads the segment. So those two are on order, and hopefully we should be 100% green if there's no other faults or ghosts that's hidden in there. Alright, thanks for following the saga. See you in the next episode.